Yeah, we can hear you. Okay.
Do you know when we're gonna have our next quiz?
Um, it's probably gonna be Friday, but not this Friday, next Friday. It's probably what, yeah, next Friday.
All right, thanks.
One second. Okay. So, any other questions? I posted the grades, so if you have any questions about that, let me know. Okay. So, last class we got up to the calculus part of, so calculus of vector valued functions. And we said that, so first we have limits, the same way we had limits before. So that is that the limit as t goes to a of r of t, where r of t is a vector, this is equal to putting the limit inside each component yeah. Okay, so right, and then we did a problem with limits. And then we said that we can define a derivative the way the derivative was defined in Calc 1, but for each component. So now we're going to have that r prime of t is going to be the limit as h goes to 0 of r of t plus h minus r of t over h. So this is going to be the derivative. It goes into each component. So this is going to be the limit as h goes to 0, f x of t plus h minus x of t over h, limit h goes to 0, y of t plus h minus y of t over h, and the limit as h goes to 0, z of t plus h minus z of t over h. So yeah, so that's a derivative. So again, the limit goes into each thing. Again, you can put the limit aside, which means the derivative is taking to take the derivative of r, you take the derivative of each one of these components, because what this is in the end, it's going to be equal to x prime of t, y prime of t, and z prime of t. So then we said we can take the derivative of each one of these components. So the derivative of t squared is 2t, the derivative of t to the third is 3t squared, the derivative of sine is cosine. And then for this problem, we have the derivative of cosine of t is negative sine, derivative of negative 1 is 0, and the derivative of e to the 2t is 2e to the 2t. And then what we said was, okay, so that's what we got up to. Any questions about this? Okay, so now we can also take the second derivative of a vector. So here they have r of t is equal to, okay, and then the first component, they have ln of t. Second component, they have t, and the third component, t squared. And they want to know what r double prime of t is. So r prime of t is going to be 1 over t, 1, and 2t. And so r double prime of t is going to be negative 1 over t squared, 0, and 2. Now, oh, they're asking also for r double prime of 3. So that's going to be negative 1 over 9, 0, and 2. Okay. So now, if you have two vectors and you add them, you can put the derivative inside. If you have a constant multiplying the vector, you can pull it out. Same thing as Calc 1. A new rule is that if we have f of t, r of t, where f of t is a constant function, so it goes into each component individually, then the derivative of this thing, so d dt of this thing, is going to be, and you use the product rule, f of t r prime of t plus r prime of t f of t. And the way you can show this, prove it, is by looking at what this actually is. So this is d over dt of f of t, x of t, f of t, y of t, and f of t, c of t. And now the derivative in each component is going to get us f of t x prime of t plus x prime of t, plus x of t prime of t dot dot in the y coordinate dot 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 in the z coordinate. And so then this becomes so yeah, you can take out the f of t's from all of them, wherever those come out. And you could also put together the x prime, the y prime, the z prime. So that will get us to f of t, r prime of t. And then putting together this side, you're going to get plus f prime of t, r of t. So that's how we can show this rule. And then you have also the chain rule, and you can show that by going into each component again. So that's what they do next. They say, oh, how can you prove this? Well, we just showed. So they go into the different components. They don't have z, only x and y. And they do what we just did. Okay, so now they're saying, let r of t equal to this and f of t equal to this. First, they want us to calculate d over dt of f of t, r of t. So like we said, that's just a chain rule. So you will have your r prime of t is going to be 2t, 5, and 0. And your f prime of t is going to be 3e to the 3t. So your d over dt of r of t, f of t, sorry, f of t, r of t. So this is equal to f prime of t, r of t, plus r prime of t, f of t. And then this is equal to, so the f prime of t is equal to 3e to 3t, and then the r of t is equal to the t squared 5t1 plus the r prime of t, which is 2t 5 0 times the f prime 3e to 3t. And that's what they end up doing. Yeah, product rule. Okay. So now for the chain rule. So again, Well, the r prime of f of t, this is going to be equal to, so the r prime is 2t, 5, and the f of t is 3 to the e 3t. So this is going to end up being 2, 3 to the e 3t, 5, and 0. And then, so then r prime f of t times f prime of t. This is going to be, so f prime of t we said was 3e to the 3t. So this is going to end up being 2, 3e to the 3t, 5, 0 times 3e to the 3t. Any questions about this?
Can you go over the last one again? The r prime of f of t.
Yeah, the r, yeah. Okay, 1 second. Oh, sorry, the f of t does not have a 3 here. No, that does have a 3 there. Yeah, so we had that the r of t was equal to t squared, 1 or something. 1 second. Um, 5t and 1. And f of t was equal to e to the 3t. Oh, yeah. So if we want to find the derivative of f of r of t, sorry, r of f of t, this is going to be equal to r prime of f of t times f of t, f prime of t, by the chain rule. So then this is going to be equal. So the r prime of t, that's equal to 2t and 5 and 0. And the f prime of t, that's equal to 3e to the 3t. So then this is going to end up being, so the r prime f of t is going to be 2, and then for the t you plug in f of t, so that's e to the 3t, 5, 0, times the f prime of t, which is 3e to the 3t. Yeah?
Thank you.
Okay. So now there is a dot product and a cross product rule, but it's the same as the product rule that we know. So the derivative of two vectors dotted with each other is the derivative if one of them dotted with the other plus the other one dotted with the first, and same thing with the cross product. So we ask us to prove that this thing is equal to this thing. So all we have to do is take the derivative of rt cross r prime of t is equal to r prime of t cross r prime of t plus r of t cross r double prime of t. This is going in the same direction, two vectors which are the same, pointing in the same direction, so their cross product is 0. So this is equal to r of t plus r double prime of t. And that's that. Okay? So now the derivative in our situation does something very similar to what the derivative did in Calc 1. So if here's a line, a curve, and I look at the derivative at this point, and so again, this line is the line r of t. And at this point, I'm looking for r prime of t. And that would be the vector pointing tangent to this line. So that's that vector right there. And yeah, so at any point you can get the tangent vector doing that. And then in order to find the tangent line at this point, if I wanted the tangent line, I would say, okay, my tangent line, let's call it L of t. It's going to be equal to the point where I'm at, so that would be r of t0 plus tv, but over here for the v, we now have r prime of t0. So again, this over here is v, and it's these vectors. And over here, this is your v, lying on the line, and then you have your line. Yeah, so again, to see how you can get this tangent line, we do what we did in Calc 1. So we take r of t plus h minus r of t0. We shrink this thing to 0. It gets, so as h goes to 0, you get your tangent lines. And again, the tangent line has the equation r of t0 plus t of r prime of t0. So this needs a calculator, so we're going to skip it. Okay, so over here they ask us for a sinusoid. So we have the following picture. So this thing is going to be traced. It's going to be the curve traced out by a point that's lying on a wheel, and then the wheel moves horizontally. So you have a wheel over here, and you're looking for one point at the wheel. And as the wheel turns on the ground, your point goes up and then comes down, because now it's back on the ground, and then it goes back up again. So that's what that does. And they tell us that the way to actually get this curve is with this r of t. So now they ask us, find the points where r of t is horizontal and non-zero. So that would be these lines over here. So every time we're up here, we will have a vector that is horizontal and non-zero. And then they want us to find the places where r prime of t is 0. And it is important to note that while this curve would not have derivatives, so if I had a curve with points like that, and I asked for the derivative at these points, those would not exist. But if you are a parameterized equation, what you're really asking for when you're asking for the derivative is the speed at which you're going at this point. So you're really inside of the curve, and you're just paying attention to that speed as you're going through the curve. And so that will have a correct derivative. So let's actually do this. So here, r prime of t is going to be equal to 1 minus cosine of t, comma, sine of t. So now if the horizontal component is 0, sorry, if the vector is horizontal, so if the vertical component is 0, then this is 0. Sine of t is 0. And if we want this vector to not be 0 completely, we need this to not be 0. So that happens at pi and 3 pi and so on. So this is pi, 3 pi. Yeah. And then if we have that they're both 0, so then if we have that r prime of t is equal to 0, the 0 vector, which would tell us that 1 minus cosine of t is equal to 0, or cosine is equal to t is equal to 1, and sine of t is equal to 0. So yeah, so this would happen at 0, at 2 pi, at 4 pi, and so on. And okay, so those are the two answers. So like we said, at pi, 3 pi, 5 pi, we would have the first answer, and then at 0, 2 pi, 4 pi, we would have these. Okay, so there are our answers. Again. And then, yeah, conceptual insight. They have a sharp points called cusps at these points, like we pointed out. And if we represented this thing as a graph, so like a curve, then the derivative will not exist at those points. But if we look at the parameterized curve and we take that derivative, then that exists for all t. And the derivative at those cups is equal to 0. And that's just because that when you're going through the curve, at that point, you're slowing down and you stop. So your derivative is 0. Any questions about that? Yeah, is this clear? Hello?
I don't really understand about the cusp. Like, I understand why we have no derivative at that point, because what we learned in Calc 2, Calc 1, that in cusps there are no derivative, but you said, the thing that you said about 0, I don't understand that.
So in this situation, so if you have a graph, so y is equal, so that's a curve. So now you're not looking for any curve, there are two ways of looking at the curve. One of them is by just thinking about it as a curve. So this is a curve, you just think of it as a curve. And another one is by going inside of the curve. So now you're inside of the curve, and now you have a meter. This would be T0, no, T1. So this is T0. And then another step, you take another step, and this is T2. Then you take another. So now you just parameterize the curve. And that's what we just did it with R of t. So just looking at the curve would be looking at the graph, and then parameterizing it would be looking at R of t. And R of t just tells you how you're moving through the curve. So if you reach a sharp point, all you really are doing, well, yeah, okay, yeah. So all you really do is going through this curve until you hit this point, and then you just go the other way. So you slow down until you stop, especially if the curve is like this, which is what it is. So this might actually not work. You would have to check. But if the curve is like this, then you go down. Your vector, your tangent vector, is always pointing out like this, but it gets small and small, then it hits 0, and then you keep going. And because of that, the derivative does exist when you parameterize the curve. So it's just a slightly different conception of what's going on. But in general, if you want to know if the derivative exists or not, just take the derivative and see what happens. Okay. So now prove that if r of t and r prime of t are non-zero, and r of t has constant length, then r of t is orthogonal to r prime of t. So before that, let's try to give a good example for that happening. So let's say you have the curve r of t is equal to cosine of t, sine of t. So now this curve looks like a circle. So here's my x, here's my y, and here is my curve. Now, the magnitude of r of t is equal to 1. Cosine squared plus sine squared. So we have the assumption, right? They want us to show that if these two things are non-zero, r of t and r prime, and r of t is constant length, so that's what we just have right now, then r of t is orthogonal to r prime of t. So we have that it has constant length. So now let's take r prime of t. This is going to be equal to cosine of t is going to be negative sine, and then cosine. Now let's dot these two. So r of t dotted with r prime of t is going to be equal to negative cosine t sine of t plus sine of t cosine of t. And this is equal to 0. So yeah, the dot product is going to be equal to 0. So that says that r of t is orthogonal to r prime of t. And conceptually, if we want to know what's going on over here, the x component has negative sine of t, and the y component has cosine of t. So if I'm over here, then I'm currently at the point 0, 1. So if I plug that in here, that would give us in the x direction 0, and in the y direction, it would give us some number over here, cosine of 1. And that will be pointing up. So that would be this vector. And as you go along this, you would get your tangent vector. So that's what this is, different tangent vectors over here. Any questions about this? Okay, and so then we have vectors like this. These are the vectors that are pointing at the curve. So this is the vector r of t. The green one over here is the vector r prime of t. And so what we just said is that they're orthogonal. So r of t is orthogonal to r prime of t. And that makes sense. This is orthogonal to that for any line. Okay. So now we are going to continue with integration. So when we integrate, we are going to integrate every component individually again. So the integral of r of t dt is going to be the integral in x of t dt, the integral y of t dt, and the integral z of t dt. So it's in each component. And okay, so then they take the integral of 1 t and sine of t from 0 to pi. So the integral from 0 to pi of 1 t and sine t. Yep. Okay, dt. So here's our vector r of t. So this is going to be equal to the integral 0 to pi 1 of t, 0 to pi t dt, and 0 to pi sine of t dt, which is going to be equal to, so the 1 over here is going to get us to pi, and then this is going to be t squared over 2, and so pi squared over 2. And then this over here is going to get us to negative cosine, so negative cosine pi plus cosine 0. Okay. Oh, and we need constants for everything. So, yeah. Yeah, anyway. Yeah, we need constants here, so plus some constant. But in our case, we don't have that if we didn't have the bounds. Okay, anyway. So, so now they're asking us to find the position where the particle has this over here, this derivative, and its location at time t equal to 4. And they want us to find the location at time equal to 4. If it's time 0, it's at 4, 1. So what they want us is they want us to first take the antiderivative of each one of these components. So r of t is going to be, so if this is dr dt, so in the first component, the 1 is going to turn into t, and then you're going to get negative 6, and then you're going to have cosine of 3t. If you take the derivative, okay, so then 3 would come out, so this is 2. And then if you took the derivative, okay, so this is plus. So then that's that plus some constant. Let's call it C1. And then for the second component, we are going to have t squared, and then we are going to have over, so 1 over 10 plus C2. Okay, so now at r of 0, we get 4, 1. So that would give us that at r of 0, we're going to have, so I'm just going to write comma, and then we're going to say t plus cosine of 3t. Let me just, 1 second, yeah, times 2. This is going to be equal, and at 0, so this is 0 now, and this over here is 0. So this is 0, is going to be equal to, plus C1, plus C1. So this now is going to be equal to 4. Okay, let me redo this so it's clearer here. So we have 1 minus 6 sine of 3t. So r of t, the d of r over dt is going to be equal to 1 minus 6 sine of 3t and 1 over 5t. Okay, so the R of t is going to be equal to t minus 2, so plus 2 cosine of 3t, and then 1 over 10 t squared. And we know that R of 0, we know that this is equal to 4 and 2, right? No, 4 and 1. 4 and 1. Okay, so then let's plug in R of 0 over here. So this is 0 plus 2 cosine of 0 plus C1. So they're constants here. So this is going to be equal to 4. That's equal to 4. Okay, so this tells me that C1 is equal to 2. Now for C2, we again plug in 0. This is 0, so that tells us that C2 is equal to 1. Okay, so now let's rewrite what R of t is. So R of t is going to be equal to t plus 2 cosine of 3t plus 2, and then 1 over 10t squared plus 1. And so then R of 4, because we wanted to know what this will be when t is equal to 4, R of 4 is going to be 4 plus 2 cosine of 3 times 4 plus 2, comma, 1 over 10, 4 squared plus 1. Any questions about this?
Can you explain again how you got C2 is equal to 1?
Yeah, so for C2, yeah, you plug in, so R of 0 is equal to 4, 1. So you plug in 0 for your t, and this is 1 over 10 t squared plus C2, and this is equal to 1. But this is 0 because your t is 0, so your C2 is equal to 1.
Okay, that makes sense. Thank you.
Okay. So, so yeah, plus 1, okay. So, yeah, so this is the fundamental theorem of calculus for vector functions. It's what we've just been showing, that if R of t, big R of t is the antiderivative of small r of t, then the integral of this thing will be that. Again, you go into every component. And then going back to the fundamental theorem of calculus, taking the d over dt of this integral, the t just drops down into this component. So in summary, we have the sum rule for derivatives that we looked at. You take out the constant, you have the chain rule, you have the product rule for a scalar valued function, the product rule for the dot function, the dot value, the dot, and then the cross product, which is the product derivative for cross products. And then we looked at r prime as the tangent vector or the velocity, and we looked at the line that is parameterized at that point and is tangent to the curve. And then we looked at integration. Okay, I think we're going to stop here. Are there any questions about this?
When you said that when we have a curve, we have two ways to see it, you mean like there's a way where we see it as the vector x of t, comma, y of t, comma, z of t, and there's also the other way with parametrization. Is that what you mean?
The x, no, so the x of t, y of t, and z of t is the parameterization. So there's one way where you have x of t, and so the t is the parameter. That's what we're And that parameterizes your curve. So here's your curve. And now your t tells you, okay, here's t1, here's t2. So it tells you where you are as you move. So as you move along, as you change t, you move along the curve and this thing changes. So that is a parameterization of the curve. You parameterize the curve into this with this t. It's a parameter to parameterize the curve. Parameterizes the curve. And then the second way to look at it is just, it's a curve. Here's a curve. And that would be y is equal to fx, or, but something like that. Now it's just a curve. I mean, it's not, there isn't another parameter. There isn't something, there isn't like, you didn't take a measuring stick and go this is 1, this, and this is 2, 3, 4, okay? If this is not clear, then try to watch some videos or read something about parameterization to get the distinction between what it means to be a parameterization of a curve versus what it means to be a curve. Okay. Any other questions?
Can you go over that tangent?
This thing again. Okay. So yeah. So if you have, so let's try to do it. What? Yeah.
I mean the tangent line problem, like.
Oh, the tangent. Oh, you want me to go over tangent line? Yeah. So before that, let me actually add something on this, which is, let's say you have the curve y is equal to x squared. So this is how it looks. Now this is a curve. It's just y is equal to x squared. We can also parameterize this curve. And that's by saying that r of t now is going to be, and in the x component, we're going to have t, and in the y component, we're going to have t squared. So does this do the same thing? Does this look, it looks exactly the same. So, and the reason is over here that your y is equal to t squared, and t is equal to x. So y is equal to x squared. But you also parameterize it. So at r of 0, you're here. This is at t is equal to 0. At t is equal to 1, you're going to be here. So now you're going along this curve. So this is a parameterization of the curve. This is the curve. Okay. Okay. Regarding the tangent line, if here is my curve, then for some point over here, the vector, the tangent vector. So here, my line over here is the line r of t. So then my tangent vector is going to be r prime of t. And if we're at t0, it's going to be r prime of t0. So that's going to be my tangent line at this point. You just take the derivative. So same thing as Calc 1. And then if you want to find the line, the tangent line, well, that using what we know already, the line at t is going to be equal to r at t0. So that's this point. That's r at t0 plus t v for some vector lying in this line. We know that this vector, r prime of t0, lies on it. So r prime of t0. So for the example that I just gave, if we have that r of t is equal to t and t squared. So now you are only in 2 dimensions, but this is still okay. Here's your curve. We can look for the tangent line at this point over here. So let's, t equal to 1. So that's going to be r prime at 1, which is going to be 1 and 2. So t, and then I plug in 1, so 1 and 2. So that's what this is. So then my line over here, if you want your tangent line, your line at t is going to be r at 1. So r at 1 is 1 and 1 plus, and then we're going to have t times 1, 2. Okay, so yeah, what?
Professor, so the curve r prime t is the magnitude of all the tangent vectors, right?
This,
So the curve of r prime of t, not the tangent curve. I mean, not the tangent line.
the tangent vector, yeah.
So the curve of r, like, how does it look like? The curve.
So if this is your curve r, oh, how does the curve of r prime of t look like?
Yeah, yeah.
Yeah. So here are your vectors, yeah. Your tangent vectors. And then you can create a curve out of them. So that would be something that looks like that. So here it's like 0, so it would be 0. And yeah, something, whatever, however it looks, yeah.
Okay, yeah. So those are the magnitude of the vector, right?
Well, if you take their magnitudes at any point, you would get the magnitude, yeah.
Okay, yeah. Thank you.
Any other questions? Okay, so I'm going to stop here, and I'll see you guys next time.